For our second lab, I observed and videotaped a coffee filter in free fall. It became apparent that the net force was not equal to zero for this lab. The system and the surroundings must have influenced the motion. Gravity acted on the coffee filter due to its mass, causing it to accelerate at 9.8 meters per second squared. The coffee filter appeared to fall much slower than I had observed other falling objects from a similar height. There must have been an air-resistant force or drag force that slowed the descent of the coffee filter. As the object was released, the gravitational field force began to accelerate the mass times gravity, which on Earth is 9.8 meters per second squared. Considering the coffee filters weigh about 3 grams, which is converted to 0.003 kilograms times 9.8 meters per second squared, the filter must have a mass of 0.0294 newtons. When the filters were first released, the drag force was negligible due to the slow speed. As the filter accelerated, the drag force also increased. When analyzing the motion with tracker, this became apparent. You can see the curved part of the graph, which represents an accelerated motion. As the acceleration decreased, eventually nearing 0 meters per second squared, this was the point where the coffee filter neared terminal velocity and the force of gravity was equal to the drag force. Using the VIDLE program, I crafted a computer model of the falling coffee filters. I weighed and entered the mass of the 3 coffee filters in the ball.m assignment statement. Then I added the values from tracker for the ball.pos and the ball.vel statements. Looking at the change in time from tracker, I entered the delta t value, which was about 100 times smaller than the motion recorded on the video. I added a value for g of 9.8 and used the unit vector for j hat, which was 0, 1, 0. After several test runs of the VIDLE model, I determined that a good value for the proportionality constant would be 0.0075. I did this by comparing the VIDLE y vector results with the tracker y vector results and adjusting the b constant until I had similar y vector values to that of the recorded video in tracker. In the while t loop, I entered the t value from tracker of 0.968 seconds. That was the time it took the filters to fall. I modified the drag force to be equal to b times the magnitude of the ball's velocity to the power of 2 times j hat. When I compared the results from tracker with the model results from VIDLE, they were very similar, mirroring the data that I had recorded on my video. This distance versus time graph compares the observed position from my video, the predicted position versus time with just the force of g acting upon the model, and the predicted position versus time that includes the drag force acting upon the model. As you can see, the results are very similar when I compared the drag force model to my actual video. To verify my results, I used a spreadsheet and graphed the acceleration versus time. I did this by placing the formula v final minus v initial divided by t final minus t initial and copied the formula into the column on the spreadsheet. Then I calculated the point where the filters reached terminal velocity. I determined this to be 5.06 seconds using the formula Vt equals mg divided by b. The constant b was determined by using the model value from VIDLE at 0.0075 in the video that I analyzed in tracker. Although the filters came very close to zero acceleration, I was able to see on the spreadsheet there was still a very small acceleration in the minus y direction of minus 0.002 meters per second, and there wasn't enough time to reach terminal velocity. As you can see in the AT graph, the coffee filter acceleration starts at g and trends towards zero acceleration. Acceleration is directly proportional to the force and inversely proportional to the mass. This explains why objects fall at the same rate of acceleration. Increased force tends to increase acceleration, while increased mass tends to decrease acceleration. As time gets larger and larger, the acceleration will equal zero due to the drag force.